So I became a nuclear engineer in the first place because I'm an environmentalist. I think that we need nuclear power alongside solar and wind and hydro and geothermal if we want to have any hope of combating the devastating environmental effects of climate change, from coal in particular. So to understand how my technology fits into all of this and how we got here and how we might move forward with it in the future, we are first going to go back in time to the 1950s in the US. So Eisenhower was president, and the United States was aglow, quite literally, with the prosperity of its post-war economic expansion. And at the same time, it had been less than a decade since the end of World War II. And the devastation in Hiroshima and Nagasaki was still very fresh in people's minds. But somehow, through a set of coordinated political, scientific, and social campaigns, people were also able to appreciate the immense potential benefits of atomic power and understand that nuclear reactions had as much potential for creation as they did for destruction. Part of this, quite unexpectedly, was due to the magic of Disney. So in 1956, Walt Disney produced a book and accompanying animated feature called Our Friend the Atom, in which he sought to demystify the science of nuclear energy, showing that it is ultimately just a fancy way of boiling water to produce steam, to drive a turbine, to drive a generator, while at the same time capturing the inherent wonder that something so small, something as small as a nucleus, could contain a power that's so very great. This campaign of Disney's, alongside Eisenhower's for peace, ushered in the start of a great age of optimism for nuclear power, and throughout the 1960s, and part of the 1970s even, nuclear reactors continued to be designed and built at a very rapid rate around the world, and in the US in particular. All of this ended very abruptly in 1979, when there was a partial meltdown at the 3 Mile Island nuclear power plant. This accident, followed by Chernobyl and coupled with rising fears about nuclear waste, effectively put the brakes on the development of new nuclear around the world. And the industry's recovery has been very slow and painstaking to this day. And so now in the world, I think we face a choice, just as we did at the beginning of the nuclear industry. If we want to continue the great scientific tradition of trying to better understand and harness the power of the atom, or if instead we want to give in to the fear caused by the failures of the recent past. My Transatomic co-founder and I, being scientists, we choose to continue, and together we came up with a new approach to nuclear power. We've developed a new type of nuclear reactor that can actually run entirely on nuclear waste. It's able to consume the waste, reduce its radioactive lifetime, and at the same time generate very large amounts of electric power. It's really quite staggering, actually, how much electricity you can potentially get out of nuclear waste. So if you take all of the world's stockpile of used nuclear fuel, so that's 270,000 metric tons, which on the face of it seems like a lot, but that's actually something that you could fit into a football field about 2 meters deep. If you take all of that nuclear waste and put it into waste-burning reactors, consume more of its electricity, you could actually produce enough electric power to power the entire world for about 72 years, even taking into account increasing demand. So I think fundamentally, we should start viewing nuclear waste as an important resource to be tapped, as a valuable material, rather than a liability to be disposed of. The design that my co-founder and I developed is actually based on earlier work that was done in the US at the Oak Ridge National Lab back in the 1950s and the 1960s, so the very early days. They came up with a liquid-fueled reactor called a molten salt reactor that ran on fresh uranium fuel. And they showed that it had tremendous safety benefits. It, in effect, couldn't melt down, even in the worst-case scenario accidents. Their original design was abandoned, however, because it ended up being fairly expensive, it had a low power density, it was quite bulky, and no one really cared back then as much about the safety benefits because there hadn't been any significant nuclear accidents. So they said, well, why would we pay so much more for a safer reactor that we clearly don't need? What my co-founder and I were able to do was change some of the materials and geometry of the design to make it much more compact and power dense, able to run on nuclear waste, while at the same time keeping all of the safety benefits of the original design. So, how does it work, is the big question. It works because there's actually a tremendous amount of the energy that's left in the used nuclear fuel. And that's because the conventional reactors that exist today are only able to consume about 4% total of the energy they could conceivably get out of the uranium. A conventional reactor is fueled by pellets of solid uranium oxide that are held in place with a thin metal cladding and put together in a fuel assembly. The metal has to be thin so that it doesn't absorb too many neutrons, but this means that the metal is readily damaged because it's literally inside the core of a nuclear reactor. And this accumulating damage, coupled with some fission byproducts that build up in the tubes, effectively shut down the reaction. So you're only able to leave the fuel in a conventional light water reactor for about 3 or 4 years total before you have to take it out. This limited amount of time it can stay in the reactor limits the amount of energy you can get out of it to just about 3 or 4% of the potential total. So in some respects, that's why the nuclear waste is such an active product, why it's so radioactive, is because there is so much energy left in it. In our design, what we're able to do is take the fuel assemblies, remove the uranium oxide fuel pellets, and dissolve them into a molten salt, into a liquid. Now, because it's a liquid, it doesn't have any long-range structure to be damaged. And also, because it's a liquid, you're able to continuously filter out the byproducts that would otherwise shut down the reaction. And because of those two factors, we're able to leave the used fuel in the reactor for essentially as long as it takes to consume almost all of its residual energy. So we can get a burnup of about 96% rather than the 3 or 4% that's possible with the other designs. And this also means that we have a very greatly reduced amount of long-lived actinide waste. So our yearly waste stream is just about 20 kilograms per year, around the size of a grapefruit, as compared to the 20,000 kilograms of the long-lived actinide waste for the conventional reactors. And it also reduces the waste's radioactive lifetime. So the majority of our waste, rather than being radioactive for hundreds of thousands of years, it's only radioactive for a few hundred years. And so it always sounds weird to say only a few hundred years, but it makes it a human timescale rather than a geological timescale. So here's a simplified schematic of what molten salt reactors look like. So up on the left, you have the primary loop that has the molten fuel salt that's flowing through it. On the far left, in the reactor core, you have a large, stable number of nuclear fission reactions that generate a great deal of heat. This heat is carried over across heat exchangers to the power production loop on the far right, where the heat is used to boil water into steam that drives a turbine that powers a generator that produces electricity. So everything on the right is pretty standard for a power plant. Everything on the left is new for a molten salt reactor. The main difference between molten salt reactors and the conventional nuclear reactors is that molten salt reactors use a liquid fuel rather than a solid fuel. So then, what's the difference between our design, our new design, and the older types of molten salt reactors that were tried and eventually abandoned back in the 1960s? So there are two main changes that we make here. The first is the moderator that's used to slow neutrons down to the right energy level to make them more likely to induce fission. We're able to use a much more compact and effective moderator that lets our core be significantly more compact and smaller, more power dense. And we also use a different type of salt that lets us dissolve in a significantly larger amount of uranium. So instead of requiring highly enriched fuel in a low power density core, we're able to run off of either very low enriched fresh uranium fuel or consume the residual fissile material that's in the nuclear waste. So with this, we've solved the problems that were plaguing the initial version of this design. I talked before about the safety benefits of molten salt reactors, so to go into that in a little bit more detail, Whereas a conventional nuclear reactor, you need a constant supply of electric power so you can continually pump water over its core to keep it from heating up catastrophically. That's what happened at Fukushima. The molten salt reactors have entirely different types of cooling requirements. So at the bottom of the primary loop, you have what's called a freeze valve. That's a plug of the same type of salt that's in the primary loop, only electrically cooled so that it's frozen solid. So if you lose your cooling, you lose your electricity rather, you lose your cooling to the freeze valve, and it automatically melts, and the salt from the primary loop drains into an auxiliary tank at the bottom. In the auxiliary tank, just by virtue of its geometry and the fact that it's no longer near the moderator, it immediately stops producing as much heat. It stops being critical, and it's able to cool itself and freeze a solid over the course of a few hours. So if it fails, it gradually coasts to a stop and solidifies rather than liquefies. So right now with our design, we've finished our preliminary design. We've raised funding for Transatomic from Peter Thiel's Founders Fund, Daniel Egerter, who's in the audience, and several others. We're also running experimental tests of some key components of our design, looking at the corrosion and radiation damage and high temperature effects to figure out how to streamline it and make it as effective as possible. And we've also gotten very good political support as well. So just this past Friday, I was speaking at the White House about advanced nuclear reactors, and at that same meeting, the Obama administration actually announced a new set of programs from the US Department of Energy that will make it significantly easier for a wide range of advanced nuclear reactor designs to get off the ground in the United States. So it was an enormous positive move from the DOE that will be extremely helpful for everyone in this sector going forward. And it's especially important because now, just as in the early days of the nuclear industry, the science isn't going to be enough. It'll require coordinated political and social and scientific campaigns and simply a sense of optimism to rouse all of us into overcoming our doubts and our fears and an attempt to move the world to be accepting of a new form of power generation. I'm committed to making this vision a reality, and I hope you all are interested in joining me in this quest. And thank you all so much.